afternoon. So we have had a little long lecture, so I will try to make up part of the time. So I am supposed to talk about the work done in theoretical astrophysics from cosmology to stars. So let us start. So the first thing is, when I was asked to talk about this, I was wondering what is the definition of landmark, which of course the organizers have not defined, and I have not seen anybody defining it. So I will also not try to define that. But so it is obviously a subjective thing. The main thing is where do you define the threshold? Because you have to define some threshold above which it will be landmark. So I thought about that, and I thought that the organizers have given me 40 minutes, so I should have something to talk about for 30 minutes at least. So that is what was the choice of the landmark. Then, of course, another problem was the theoretical astrophysics. Now, when we joined the institute, that time, of course, the theoretical astrophysics and things were well defined, because the other people had to build instruments and get data and so on. But now, after 90s, things have changed. Once the internet came, almost all data of astronomy is available, and anybody can use that. So there is no real difference between now theoretical astrophysics and the other things. So, of course, in consultation with the organizers, I decided that the definition of theoretical astrophysics is whatever is done by the members of theoretical astrophysics group. Now, that itself is not well defined, so I have some loose definition of that, and hopefully we'll stick to it. And I am hoping that the work done, of course, there are other theoretical works done outside the theoretical astrophysics group, because some of it was already covered in the previous talk, and I think I will leave the rest. So now, of course, the choice of the landmarks is obviously biased, and I apologize in advance to my colleagues in case I miss something. So that is there, and I have selected about, my predecessor had a long list, so I have only about 20. So hopefully I will be able to finish faster. So we will start, of course, as usual, start with the history. So the research in theoretical astrophysics at TIFR was initiated in 1967 to complement the observational work in radio and X-ray astronomy, about which we already heard before lunch. Now, the group formally, in some sense, began when MS Vardhya and SM Chitre joined TIFR in 1967. They were followed by K.S. Krishnaswamy in 1970 and J.V. Narlikar in 1972. So these were the four founding members of the theoretical astrophysics group. Now, before joining TIFR, MS Vardhya had done pioneering work in stellar evolution and also in opacities in stellar atmosphere. That time there was some problem about that people felt that opacity, whatever known sources of opacity were not enough to explain the solar atmosphere. And it was later on proposed that H minus is the missing thing, that is the hydrogen with the extra electron. So Vardhya had done important contribution to that, and in fact the first tables of opacity with H minus were made by Vardhya. In fact, I also used them in 80s. Then Krishnaswamy had given his well-known T tau T temperature and optical depth relation, which is still extensively used in all stellar evolution calculations. So in that, for calculating the structure of the atmosphere, we need an additional equation because it is not in thermal equilibrium, because it is being radiated out. So that he had given this fundamental relation, and even today all stellar evolution calculations are using it, and more importantly, it is also known as Krishnaswamy's T tau relation. And Narlikar, of course, is well known for his work on steady state cosmology. So that was this people's thing. And then, of course, there was S.P. Tarafdar, who was actually the first student to complete PhD in theoretical astrophysics in 1972 on sources of opacity in late type stars. So Tarafdar actually joined TIFR in 1963, before the theoretical astrophysics existed. And initially he was working with R. Pratap. I don't know how many of you know him. He was a plasma physicist. He moved to PRL later on. And S. Ramadurai also had joined TIFR in 1963, but his PhD was in cosmic ray physics, and after that he moved to theoretical astrophysics group. So that was the beginning of the theoretical astrophysics. So I will now outline some work in different areas. So I have tried to cover, of course, I have about 20 odd works, but they are spread over different areas. So of course, there will be some variation between different things. So Narlikar established a strong group working on cosmology, general relativity, and quantum gravity. So of course, the most notable contribution in this area is the detection of gravitational waves, which has already been mentioned in the previous talk by a pair of merging black holes in 2015 by the LIGO collaboration. This is of course not a theoretical development, but nevertheless theory played an important role in that. In particular, the templates for the whatever wave pattern that you see were calculated theoretically, and A. Gopakumar from DA has, and of course there are many others from TIFR who made some valuable contribution in this, and this opened a new window to the studies of astrophysics. So that is of course the remarkable thing. And this was followed by detection of gravitational waves from merger of a neutron star and a black hole. And this, because of the involvement of the neutron star, this was also visible in the electromagnetic waves, and there was a huge number of observations in that, and that gives rise to the so-called multi-messenger astronomy. Of course, this is not the first instance of multi-messenger astronomy, because we had neutrinos and cosmic rays even before that, apart from electromagnetic waves. So that is the thing. Now I will move to other things in cosmology. So one of the important thing now, Kaushik probably was not strictly a member of theoretical astrophysics group, but I have included him because I was sure this work will not be included in the DHEP discussion. So Kaushik and McClelland in 1972 obtained an upper limit of 8 electron volt on the sum of the masses of possible light neutrinos by considering the effect of gravitation on the thermal background neutrinos on the expansion of the universe. So this limit was basically based on the then whatever estimate was there on the deceleration parameter of the universe. So that is an important thing. Then another interesting thing was Padmanabhan and Chitre 1987 explored the effect of bulk viscosity on the evolution of the universe, and they demonstrated that this can lead to solutions which are like inflation. So of course, I am not sure how the viscosity will come there, but nevertheless, it is an interesting idea. And in a similar vein, the next thing is Pankaj Joshi, TP Singh, and the group have been extensively working on the validity of cosmic censorship conjecture. Now that basically says that all singularity and general relativity are covered by an horizon. So they have found some counter examples where they have found many solutions of Einstein equation where the singularity is visible outside. But the issue is still open as to whether any of this can occur in realistic situation. So now we move to gravitational lensing. Chitre and Narlikar were instrumental in starting the work on gravitational lensing, which is basically based on the gravitational deflection of light by massive objects. So basically the gravity acts like a lens, and you can get some magnification and even multiple images and so on because of that. So this has actually evolved into an indispensable tool for studying the universe at large scale, in particular the dark matter, because the dark matter does not have any other effect other than gravity. So that can be studied by this means. Now they were later on joined by Narasimha and Kandaswamy to form a pioneering group for modeling multiply image lens system. And in fact, TIFR Central Workshop even produced a model of gravitational lens, which Narasimha very methodically worked out to get the shape of the thing to get the correct image. So that is now one of the first sources to be studied was PG1115 plus 080. That is the second multiply imaged confirmed gravitational lens reported to the quasar at a redshift of 1.72. And initial observations that found 3 images, and they said that there should be a 4th image, and they also predicted what would be the galaxy which will produce that image, and later on all these things were found. So this is just an image of this images and that galaxy in between. So then apart from that, they also modeled these other sources, MG2016 plus 112. This is another multiply image quasar at a redshift of 3.23. So they predicted that a massive galaxy cluster as a lensing agent. This was in 1987, and this cluster was actually discovered by ASKA X-ray observation in 1994. So this is again some image of that. So basically this A and so this A, B are the two sources and two images, and the A1, B1 are actually the line forming some vision from that side. So it's just extended form of that source. And C and D are the lensing object which form the image. So that is the thing. Then of course, now there it was also observed that the lensing model with extended mass things generally predict an odd number of images, while observation largely found only even number of images. So this was, they had proposed that this could be because of the presence of massive compact object at the center of the lensing galaxy. So that was one of the things. Then of course, they were also among the first people to point out the effect of the so-called micro lensing, which they actually called it a millilens. So this is basically when a small compact object comes exactly in between us and the background source. Since all these things are moving with respect to each other, so this will happen only for a short period. So you will get a suddenly sharp peak in the intensity. So that is called the micro lensing. And of course, you can infer the mass of the object which is forming the thing, and this can be used to study even objects which are not otherwise visible, like black holes or even planets and other things that are too faint to be seen. Then they also predicted the formation of Einstein ring and giant arcs, which are, of course, they called it gravity ring at that time. Now it is called Einstein ring. And then, of course, there's one other important work, which was the rigorous general relativistic. So these were all, of course, you need the relativity, but it is all still weak field approximation. So they computed the thing in the real strong gravity. So full general relativistic treatment of lensing in an idealized spherically symmetric configuration. And this was work done by Veerbhadra et al. In 1998. And they studied Einstein ring, critical curves, and all the things in the system. And they also obtained a rigorous relativistic treatment of the complex system of images. Now, this study was in fact ahead of its time, because in 1998, nobody actually thought that those things can be seen. So these are very large number of images very close to the source, and also people did not think that these things will be relevant. But now with the Event Horizon Telescope, many of these effects have been actually seen. Of course, that is a much more complicated system than what they considered, but nevertheless, all the effects have been seen. So that is about the gravitational lensing. Now I'll come to the high energy astrophysics. So I have put a few works. These are all in chronological order. There is no specific thing. So Sandeep Chakravarti, who was at TIFR for some time, studied shock solutions for stationary, axially symmetric, and rotating adiabatic flows in the accretion disk of wind. So this is basically high energy astrophysics is mostly the study of accretion disk around compact objects like black hole, neutron star, in some cases white dwarfs. So he studied the shock formation in this thing. Now theoretically you can have 4 locations where shocks are possible, but he found that all of them are not physical. So depending on the situation, either 2 or 3 are acceptable. So for the accretion through wind and accretion disk around a neutron star, there are 3 possibilities, while accretion to a black hole from the accretion disk, it is only 2 of these locations are feasible. Unfortunately, the theory cannot distinguish between these 2. So both are equally possible. So then another thing, this was the adiabatic thing. Now it was extended to include the effect of cooling, and they used the smooth particle hydrodynamics to simulate the thing, and of course to find that given angular momentum of the flow, the shock wave undergoes a steady radial oscillation with the period roughly equal to the cooling time. So these oscillations might be responsible for the quasi-periodic oscillations which are seen in many black hole sources and neutron star and other things. So these are pretty common in many of these things. So he had given some possible origin for some of these things. So that is that. Then we come to the next thing, that is Pranav Ghosh and Abramovich, 1997, they critically examined the strength of the magnetic field threading the horizon of accretion disk-fed black holes in quasars and radio galaxies. Now, they pointed out that the strength of the magnetic field in the current numerical simulations was much smaller than what was assumed earlier, and hence this has to be accounted for. And if you include that, then it reduces the strength of the well-known Blandford-Zenek process, which is one of the process for expecting rotation energy from the black hole. So as a result of this, this process may not be adequate to account for the strongest double radio sources accreting at far sub-Eddington rate. Of course, for a medium and weak source, it will still be enough. So that was that. Of course, Pranav had done a seminal work on accretion disk, but that was before he joined TIFR. So then Alak Ray, Purnam Chandra and their collaborators, 2010, reported a relativistic type 1 PC supernova without detected gamma ray bursts. So the long duration gamma ray bursts are generally believed to be due to the death during the death of the massive star. So once the massive star finishes all its fuel, then it undergoes the collapse and leading to a black hole or whatever. And that time, of course, a lot of energy is emitted, and that also results in a relativistic outflow, which basically manifests in the gamma ray pulse. And it also gives a long-lived radio afterglow. So this gamma ray pulse is along the relativistic outflow, so it is a collimated thing. So unless it is pointing towards the Earth in some reasonable angle, you will not see it. So there is definitely a chance that you will miss that. And apart from that, even the duty cycle of the gamma ray satellites is also limited, so there also can miss things. So this was one of the first examples, or probably the first example of such a event. So that is there. And now I will come to the final thing, that is the stars and the interstellar medium. So Prasad and Tarafdar, 1983, they investigated the possibility of UV radiation filled inside the dense interstellar cloud. So basically, when you have a dense interstellar cloud, because of the optical thickness, the stellar UV radiation cannot penetrate to that. And therefore, of course, people were not expecting that UV will play any role in the chemistry in that deep regions. So they pointed out, and of course, the cosmic rays can penetrate that, and cosmic rays were supposed to drive this. But they reasoned that the cosmic ray will, since the cosmic ray will lead to ionization, but then this electron will again recombine, so that will give rise to a UV radiation. And because of that, you can actually have a UV flux inside the cloud, even though the outside thing cannot penetrate there. And they calculated that that will be enough, and to get a chemically significant UV flux to be present there. And in fact, they calculated that some of the reactions can proceed at a significantly higher rate, up to an order of magnitude higher, because of this effect. So that was an important contribution. So now, then of course, we come to the actual stars. So the work in heliosismology was initiated by Chitre in 1975, and a number of important results have been obtained. So I have listed a few of them. So one of the things is the depth of the solar convection zone. So in the outer 1/3 of the solar radius, the energy is transmitted by convection, and the depth of the convection zone is an important parameter. And in fact, it very sensitive to the various input physics that goes into construction of the stellar model, in particular opacities and others. And apart from that, also helium abundance. Now, helium is, of course, the second most abundant element in the universe and also on the sun. But the helium abundance could not be measured from the photospheric lines, because helium, being a noble gas, it doesn't form a line at a low temperature of 6,000 degrees of the solar atmosphere. So the helium abundance was actually determined using heliosismology. Of course, there were estimates from coronal lines and all, but they are very uncertain because they are still very dynamic region. So now both these things can put a strong constraint on the solar models. And of course, these were not the first measurement of these quantities, but they are the most often quoted values. Now, apart from that, the inversion of rotational splitting was carried out to study the rotation rate in the sun, inside the sun. Of course, on the surface, we know that there is a differential rotation with equator rotating faster than the pole, but we did not know before that what happens in the interior. And in fact, there were many conjectures that the core could be rotating faster than the surface, because basically, because of the energy, because of the angular momentum conservation, the young stars will have very fast rotating thing, and slowly the rotation, the angular momentum is lost. The loss happens to the surface, so it was thought that the core may be rotating faster. And in fact, that had some implication on the test of the relativity also. But nevertheless, the heliosysmic data allowed us to first time actually measure the rotation rate in the interior. And of course, we didn't find any fast rotating core there. In fact, the core is rotating slightly slower than at least the equatorial region on the surface. So there are, in particular, the important discovery of these things was there are two shear leads. One is near the surface where the rotation rate increases with depth, and another is near the base of the convection zone, which is referred to as the Tecock line. So that is the region where the differential rotation goes over to a solid body rotation in the radiative region. So that is a sharp transition there. And this was, of course, totally unexpected. And the properties of this region were studied, and also the temporal variation in these properties were also studied. So I think that I have a picture of that. So this actually shows the rotation rate as a function of time and latitude. So this is basically you have subtracted the average at the given latitude from that. So this is basically a residual. So if you see the red or blue, whatever thing, that is the faster than average rotation, and the blue ones are the slower than average rotation. So you can see that there are formed these bands which move towards the equator at low latitude, and towards the high latitude they move towards the pole. So this part was actually pointed out by us first time. And then the top, this is using the Gong data, and that is using the MDI data, that doesn't matter. And the top panel also has these black dots, which are the position of the sunspots. So you can see that this bends coincide with the position of the sunspots. So they definitely play an important role in the solar magnetic field, because sunspots are the sites of the magnetic field. So let me go back there. So now there is another implication. So around 2004, the Esplund and their colleagues pointed out that the heavy element abundance in the sun has to be reduced significantly by a factor of 1.4 or so. They claim that that is because all the earlier estimates were based on the so-called 1D model of the solar atmosphere, which basically is the spherically symmetric thing with some effect of turbulence and all built in. While they use the so-called 3D atmospheric models, which incorporates the turbulence inside there. And they found that using that, it reduces the abundance. And so, but then it was soon found that these models with lower, because once you reduce the heavy element of abundance, because they contribute to the opacity in the solar envelope. So because of the opacity, the depth of the convection zone changes, and these low abundances are not consistent with the solar model. And there was a detailed analysis has been done using both opacity, equation of state, etc. And it was shown that the low abundance models are not consistent with seismic data. Now, since then, a number of independent measurements of the solar abundance have been performed, and things are now moving upwards slowly. Though, of course, even Esplund and their colleagues have also increased their estimate to some extent, but the thing still remains. Now, more recently, of course, there is a data from the Borex-CNO experiment, which has been able to estimate the flux of the CNO neutrinos that should be directly proportional to the heavy element abundance. And that flux is also consistent with the higher abundance, though of course the error bars are still large, so you cannot rule out the other things also. So that is the status. Now, let me see. So that is about the sun. Now, more recently, the study has been extended to other stars, mainly for using the data from the Kepler satellite, which observed many stars for a period of slightly more than 3 years. And Shravan Hanasoge and his colleagues have detected the latitudinal differential rotation in the convection zones of about 40 sun-like stars. And all of them have the sun-like differential rotation, that is equator rotating faster than the poles. And for the most significant detection, the equator rotates about twice as fast as the mid-latitudes. So this, of course, will have implication on the theories of angular momentum transport in stellar interior. In a similar way, the radial differential rotation has also been detected in an early red giant, this KYC 7341231, where the core was found to rotate at least 5 times faster than the surface region. So this, so of course, people were expecting that in the sun, but in sun didn't happen. But it has been found in the, of course, in the red giant, the core is extremely small. It has already condensed during the later stages of evolution. So this result can constrain the angular momentum coupling between the core and the envelope of the red giant. So I think I will stop there. I think I have made up most of the time. So, okay.